Hello everyone, my name is Dániel Horváth, and I'm going to present you our work published in TRO titled Object Detection using Sim2Real Domain Randomization for Robotic Applications. The motivation behind our research is that in new generation intelligent manufacturing, we try to combine artificial intelligence and manufacturing science, but many times artificial intelligence, namely deep learning-based models, cannot we don't really have enough data to train them. And then we need some kind of methods, for example, Sim2Real transfer learning to transfer the knowledge from simulation to real life. And our main contributions are the follows. First is the Sim2Real domain randomization method. And for object detection, our real-world data set, which we needed to create for the industrial setup, a confusion matrix, which was tailored to object detection, and the real robotic implementation. Our results are 86% and 97% MAP score for zero-shot transfer and one-shot transfer. And we have a thorough ablation study for finding out the key factors of the data generation process. The pipeline is that we have a 3D models of our objects, which is quite common in industrial setup. And we generate, we put them in a simulation in randomized positions. We use gravity for further randomization. We randomize the camera position. And after the pictures are taken, we also have a post-process method for further randomization. As we know all the positions, we can just automatically annotate the images, and creating the training and validation data sets in the synthetic domain. We use the training data set for training, where we have a convolution network, and we train the model. And for evaluation, we also use a test data set. For data generation, you can see on the left side a sample of the generated synthetic image. On the middle, you can see different kinds of textures that we used. And on the right image, you can see further images. Also here, we detecting the orientation, but that's not that's a further research, which is ongoing research right now. For the training, we can have a convolutional neural network. We use YOLO v4, but we also test in faster RCNN, but it doesn't really matter which convolutional neural network that we use. It's better to have a pre-trained model that we can train on synthetic images, are generated synthetic images, and then with the domain randomization method, hopefully it's going to work in the real domain. This is the second part, is the Sim2Real transfer. For the industrial data set, we needed to have a model which is capable of differentiating between detecting really similar objects in size, color, and shape and everything, but also at the same time differentiate between objects with same characteristics, for example, in the body and the bonnet in the middle. And so we created this data set for taking into consideration these factors. And the result, we have a zero-shot transfer result, which is quite decent in general. But if you see the different object, there is some objects which it's not working that well on them. And the main reason that we figured out using this altered version of the confusion matrix for object detection is that, for example, in the place of bonnets, 62 bonnets were misclassified as body. And thanks to this altered confusion matrix, we could detect that it's the underlying problem. And in one-shot transfer, we used only one real image with 10 objects on it, all the 10 objects on it. And we could achieve 97% MAP score. And you can see on the right as well that most of the samples are on the diagonal. And what it means that probably the difference between the bonnet and body was somehow lost in the Sim2Real transfer, but introducing one real image, which I think it's not a big deal in an industrial scenario to have only one image of the object. Obviously, always it's good to have without them, but one image, I think it's feasible. This problem could be overcome. So qualitatively, there are two examples on the left, and completely accurate example on the right, and the accurate example. As you can see that on the bottom left, that the destructor object which had the same characteristic as the body object was misled the model and classified as body. For the ablation study, we had a thorough ablation study with just two examples of them. On the left side, you can see without texture, without post-processing, the model scores around 10%, which is really useless. But with them, basically with our method, we have 85% MAP score. And on the right side, you can see how gravity, how randomness in position, and how the bounding box calculation affects the result. And we have a robotic application where we use 3 different types of objects, and the robot needed to to find them on the camera image and then grasp and put them in different positions. And for this, we have a video as well. As you can see here, also we have the orientation estimation as well, and the object, the model can very robustly find the pieces, and then the robot. This is a different robot, but we can place the objects. We tried it in this Frank Kamika robot, but also in the UR5 robot that you could see on the picture before. And finally, some future work. We plan to use adversarial training to make the method more robust, but also experimenting in other domains such as reinforcement learning. And we also plan for some kind of productization, that there would be a user-friendly interface when the industrial partners can just train their own models and use them on the robot. So that was it. Thank you very much for your attention, and see you in the conference. Bye.